starting the stream, and we'll double check, make sure it is recording the voice. Okay, it's all good. All right. So to get this assignment done, I'm going to start up my. I'll refer to my notes because I cannot remember those equations. So I'm going to start up my notes just so that I can refer to the equations. Let's see, what is the quickest way to do it? Modules. There we go. So we'll need to refer to addition, where the structure of the code is, and I'll also refer to subtraction so that we can tell the differences between addition and subtraction. Okay, so we go to the HTML page in both cases, and then we switch back to, oh, I have it in the other window right there. So we have Logisim over here, and we'll just go ahead and design our subtractor over here. Zoom in just a little bit because at this point we can afford to. So we'll have we'll have 3 pins. 2 of those will be 3-bit wide and 1 is 1-bit wide. So here's our X, here's our Y. They're both supposed to be 3-bit wide. So we'll go back and adjust that, 3-bit wide. And this one is 3-bit wide as well. And this is our Cin, but in the subtractor it's called Bin, binary borrow in. So now we have all the input pins. I'm not going to draw the output pins until we get to the output part. So we'll only have the input pins. So the first thing you might need to do is to generate the P's and the G terms. So when you go back to the notes, which is in the other window, for subtraction, the P and the G terms are defined just slightly differently compared to the addition. So in subtraction, the G terms are defined to be the negation of X and Y, and then the P terms are defined as the negation of X or Y. Okay, so this is where a multi-bit gate is really, really handy. So I will pull a AND gate here and pull a OR gate here. Okay, we have to do some adjustments here. We changed the number of bits to 3. The size is just for display purposes, so it's not a big deal. The number of inputs will still be 2. And do the same thing with the OR gate. 3-bit wide, narrow, and 2 inputs. Okay. You can also see how these dots are no longer blue in color. They're now just a little black dot, which means they are multi-bit. Yeah, so the color actually has implications. So now we just hook up this wire over here, and okay, I did a little bit more than that. Okay, there we go. Just this wire, and then have this wire to hook up to this input here. So what is coming out of this AND gate will be 3 bits, but those are my G terms. So I have G0, G1, and G2 coming out of this one as one single bundle of multiple bits. So I can do the same thing with the OR. Okay. Oh, I forgot one thing. Yeah, I forgot that. This is great for addition, but it's not good for subtraction. Because subtraction, okay, let me go back to the subtraction notes here. So in subtraction, we want the X to be negated and the P and the X to be negated for both the P and the G's. So that means, in getting back to Logisim, I want this to be negated. I also want that to be negated. Okay, I forgot about that. Okay, no big deal. So we just click on this thing here and just say negate the top. We click on this thing and we say negate the top. So now we can just reconnect things a little bit. There we go. So now we have the P's and the G's for subtraction. The rest of this is the same as for the adder, because the only change from an adder to a subtractor is how you define the P's and the G's, by negating X. The rest of the design is identical compared to an adder. Okay, so I'm going to label things a little bit just to remind myself. These are the G's, these are the P's, okay? And the rest really depends on how you want to do it. Okay, the way I want to do it is, in this case, I'm going to add subcircuits for K1, K2, and K3, or T1, T2, and T3 in this case. So this is T1, and if I switch back to the nodes, this is not going to show me what T1 is going to look like. but T1 has exactly the same look and structure as K1. So I just have to look up what K1 looks like. So instead of T1 here, instead of K0 here, we'll have T1 and T0. Okay. So oops, I always use the wrong kind of switch. There we go. So now it is up to you to design the interface into these subcircuits. Now the subcircuits can also make use of multi-bit inputs. Okay. So in this case, I have this multi-bit input being my G, and I can have duplicate this one to be my P's, and then have one single pin for K0. That's perfectly okay. No one says you cannot use multi-bit pins for the subcomponents. So this is my G, this is my P, and this is K0, or T0 in the case of a subtractor. So now I can look back at the equation and say, what is T1? T1 is G0 or P0 T0. Okay, so it's always okay to copy this. Go back here, get myself an OR gate, label it using that equation, and then change the rest. Okay, one single bit is right, but I only need 2 inputs in this case for the OR. And we'll just kind of arrange it here. And this time you notice that we only need G0 out of G, we only need P0 out of P, so we'll use a splitter to do that. In other words, it is not avoidable to use splitters. So you can either use splitter in your main design, or you have to use splitters in the sub design. But this time I can change the fan out to only 1, but the bit width has to be 3. And the only bit I want to display or to use here is going to be bit 0. So I'm going to use a none for bit 1 and bit 2. So now the splitter only is going to split the 3 input into 1 output, which is bit 0 itself. Bit 1 and bit 2 is not even represented as the output of the splitter. Are there any questions about this approach? I'm just not using bit 1 or bit 2 of the input pin. I'm just saying that, oh, okay, just give me bit 0. I don't need the rest. Okay. So looking at this equation, I also need an AND gate. So now I pull an AND gate, change the size, change the number of inputs to 2, and that has to take care of P0, K0. So we have it quite handy here, because this one just needs to go here, and this one just has to, oh, okay, that doesn't look good, but it's still okay. That's my subcircuit. So you can use a splitter inside the subcircuit, okay, which kind of makes it look clean. When you look at the main design, it's going to look cleaner, using this method. Okay. So when this is all done, I'm going to go back, right-click on it, and say Edit Circuit Appearance. There are a few things I want to do. One is to designate this one as T1, because otherwise, they all look the same. I cannot differentiate which one is which one. And I also want to label which one is G and which one is K0, T0 actually. And there's one more thing I forgot to do, because there's no output pin here. So let's make an output pin. And the output pin should be my T1, so I'll label it as such. And if I switch back to Edit Circuit Appearance, now we have that pin kind of like going off on its own. So we'll go ahead and get it back to where it's supposed to. So we'll go ahead, okay, I selected too much stuff. Go ahead, move this one back here. Okay, now we have the subcircuit. So are we okay with this so far? Okay. If there are no questions, I'm going to make the next one. So this time we can look at T2, and we can copy certain parts of T1. So we go to T1, and we just select the stuff that we want to copy from. Okay, so oops, Control D doesn't work. It's Control C and then Control V back here. Control V. Oh, it's not pasting. There we go. One more time. Control C, Control V, there we go. All right, but this time the splitter needs to split a little bit differently because the equation has changed. The equation of K2, or T2 in this case, is this equation. So we just do a Control C, go back here, pull a OR gate, and label it this way. So this way I can refer to just the label to figure out the rest. And make it narrow, 3 input in this case, and the rest would also have to change. The fan out is now 2 because I need bit 0 and bit 1, but I don't need bit 2 to be exposed, so I just limit myself to these 2 bits. And then we can get rid of this splitter because I can just duplicate this splitter and put it here. Are there any questions at this point? So this approach is not optimal from the perspective of I have more splitters than I really need, but at the same time the interface between the main components in main is actually really clean because every single thing is multi-bit except for the T's. So looking at this equation, I have G1 by itself going into the input of the OR, and then we need 2 AND gates. So we'll pull an AND gate, make it narrow. The first one only has 2 inputs, like so. And then we have to figure out which 2 inputs, P1 and G0. So here's G0, and here is P1, like so. And then the last one is an AND gate that has 3 inputs. So Control D, and make this a 3 input AND gate, and we need to use T0, P0, and P1. There we go. All right. So the output of the AND gates go into the input of the OR gate, and then the output of the OR gate is the actual result. We'll give it an output pin, and then label the output pin T2, because that's what it is. All right. Right-click, edit circuit appearance. Like before, I just need to remember this is the circuit to calculate T2. This is our G, and this is our T0. That's all I need in order to make use of this correctly. We have one more to do. So we go to Circuit, Project, and then we just add Circuit. This one is T3, which is the biggest one. And we'll go back to T2 and just copy and paste a little bit. Copy, paste. And this time we need a full split. So we need a 3-to-3 split in both cases. We need a bigger OR gate this time. And then we look up the equation for T3. You can see that I'm copy and pasting from the adder discussion because they are the same. The structure is the same. It's just that that K0 for an adder is now replaced by T0 in the subtractor. All right. So we need G2 will go into this one. It's a 4-input OR gate this time. So we will have G2 all by itself. Okay, that's done. The second one is a 2-input AND gate. So we'll put AND gate, change it to 2 inputs, make it smaller. And it needs to get its input from P2 and G1. Here's P2 and G1. And then the output of this goes into the other one of the inputs of the OR gate. The third one is a 3-input AND gate. So we pull this AND gate, change it to 3 inputs. This time we need G0, which is here, P1, and P2. There we go. and this output goes to another input of the OR gate, and then we have the 4 input AND gate as the last one, and that is going to take T0, which is labeled as K0 in the formula, and then all of the P's. Okay, so we got this one already here, here, and then we just need to get P0 to go to the last input, and then the output of this goes to the last input of the OR gate. The output of the OR gate is now our actual answer, which is T3. So hook it up, call it T3, and we're done. So now we right click on T3, edit circuit appearance, just do the same thing that we did before. Call this one T3, label this one G, label the last one T0, because what is left is going to be P, so that's why I only need to label 2 instead of all 3 of them. Alright, so now we go back to main, go like, hey, it's pretty easy now because we have T1, T2, and T3. Okay, maybe scroll down a little bit. But they all have the same inputs. B in, which is T0, now goes to all 3 of these. Goes to this, goes to this, and it goes here. And then the output of G, the AND gate, would also go to all 3 subcircuits. So this is the reason why I make the subcircuits having a uniform interface. Is from the main design perspective, it looks very uniform. Obviously, you don't have to do it this way. You can use any method that makes it work. Okay. Drop the mouse at the wrong place. There we go. So now when you look at T1, T2, T3, and also T0, I need to make a bundle of 3 bits. So now we use the wiring, pull a splitter, but we have to change the direction because we are now merging from left to right, and we're dealing with 3 inputs. So now we have a splitter that looks like this, and the first one to go in is B in, which is actually our T0. So this is T0, here's T1 as labeled, and here's T2 as labeled. What about T3? T3 is our borrow out. So T3 does not connect to that splitter, and instead it connects to an output pin. So I'm going to put all the way here. Okay, there we go. Okay, so first thing first, okay, we have to get the result first. So the result is the applicate. So we are looking at the exclusive OR between X and Y, and then whatever that output is, we have to exclusive that with the borrow bits. So we go to the gates, and we look up a exclusive OR gate. Change the design a little bit, and it has to be a 3-bit gate because now we're using multi-bit logic. So the first one comes from X, the second one comes from Y. So the output here is now the OR of XY, but that's not the actual result that I want because I need to apply another exclusive OR gate to exclusive OR with the borrow bits. So now I duplicate this one and make use of my borrow bits as one single 3-bit bundle into the second exclusive OR gate. These 2 exclusive OR gates are multi-bit gates, and that's why I can do this. The output of this is now my difference. So I connect it here and change data bits to 3 and label this as D, for difference. And we can now also pull this pin all the way up and make an output pin for this wire, and we'll call this one B out for borrow out. So we'll call this one borrow out, like so. So my circuit should be done. And we are looking at the first test case at this point. Let me zoom out a little bit. We are looking at the first test case, which is 0 minus 0 with a borrow in of 0, has a result of 0, a difference of 0, and the borrow out is 0. That makes sense. So the first test case I want to test it is x and y both being zeros, but borrow in being a 1. And you can see it is correct, because it is the same thing as 0 minus 1, which is 1, 1, 1 with an overall borrow. Is that okay? If I make a 1 here or 1 here, well, excuse me, if I make a 1 here, that will make it into a 0, because it becomes 1 minus 0, whatever that is, minus 1 again. But 1 minus 0 is 1, 1 minus 1 is all 0. That's why you see the difference itself is 0, and the borrow out is 0 as well. Is that okay so far? Okay. If I make this a 1, that 1 should appear here. And if I make a 1 here, it should have a borrow, overall borrow, and that 1 turns on too. So the design works as far as I could test it at this point. Are there any questions about this particular design? It's just one of many ways to get it done. It's not the only way. So the focus today, with this design is the use of multi-bit gates. This is multi-bit, this is multi-bit, this is multi-bit, this is multi-bit as well. So that makes the main design a lot cleaner. The sub-design or the sub-circuits, they're not too bad. We just have some duplicate splitters, because I have a splitter here, and also a splitter here, as opposed to having just the splitter splitting ones, but feeding into the circuits differently. But then the sub-circuits would not have a uniform look, because they would have a different number of input pins. And it's also easier to hook up the wires incorrectly. Do you guys see how why that would be the case? If you make these sub-circuits, having one individual bit for each G and each P, then each time you wire up the connections, it is a chance of making a mistake. As opposed to doing it this way, then you the connection in main cannot be wrong that easily, because you're only hooking up all the G's into the G port, all the P's into the G ports. And it's not likely to make a mistake. But when your sub-circuit, like T3, has 7 inputs, then it becomes much more likely to hook up the wires incorrectly. So that's partially why I chose to do it this way. Is that okay so far? No? Good? All right, cool. So that's it. That's just my little demonstration of how to do the homework. If I were to turn this into an adder again, it becomes very easy now, because I just have to go to this gate and take out the negation of the top, go to this gate, take out the negation of the top, and wire this thing back up, because otherwise it won't stay wired. Okay, that becomes an adder again. Okay, it's really that's the only difference. And one of the submissions actually has a extra bit here to turn this entire design from an adder into a subtractor by using one single bit to control, am I an adder now, or am I a subtractor now? That is doable as well. But it really illustrates one thing that is kind of strange, is how an adder is similar to a subtractor. And I think that's kind of cool. So are there any questions about the solution to this particular homework assignment? No questions? Okay, if there are no questions, I'm going to turn off the streaming and turn off the mic, and then I'll just try to answer your questions of the current homework assignment, which is the parsing of scientific notation in base 10.